which all of us, kind of admire and want to have, an institute inside a university system. And CTP Jamia has been, this institute existed for a while now and has been doing very well. His interest, particularly, he graduated, he did his PhD from SPS, JNU, on aspects of foundations of quantum mechanics. And then he moved on for a postdoctoral fellowship at the Institute of Math Science. And then he joined Jamia. And since then, he has been working there. Professor Qureshi is really very prolific in his subject. And one thing I really appreciate about him is that even at this age, he writes lots of single author, which is very aspiring, And with that, I think I will like to invite him for telling us about the new excitement, whatever he's excited about on this subject of quantum entanglement, quantum information, and foundations of quantum mechanics. Tabish, please, please go ahead. The stage is yours.
Thank you, Sarin. So is it visible?
Yes, very much, very much.
Yeah, I think now it's better. So thank you for this very nice introduction. And after Soren's comment, I realized that, oh yeah, that he's talking about my age. So it's not, I'm not young anymore. So anyway, so.
Oh, no, not that way. Your academic age.
Okay. No, I was just kidding. So today I'll be talking about this subject which has been debated for many decades. So something called delayed choice quantum eraser. So today we'll discuss, and I'll try to explain how one can actually better understand this subject, which has been very controversial, and you will see that a lot of blogs written on it. In any book on foundations of quantum mechanics, you will see this topic being discussed. So I'll give an introduction to this subject, and then I'll try to explain how one can understand it better. Okay, so outline of the talk is, first I'll explain this double slit experiment, which you all know already quite well, and wave particle duality, then this concept of quantum eraser, and then this subject of this paper, delayed choice quantum eraser. So consider this very simple experiment where you have say massive particles, and there's a double slit, and there's a screen here. So suppose one of the lower slit is closed, only the upper slit is open. So when these particles travel, so only particles which are directly in front of this one slit, they'll pass through. And of course, I have drawn them very close. So this screen is actually far off, and these slits are much closer. So you will not see one single point. You will see rather a distribution of points where this particle hits on the screen. On the other hand, if you close the upper slit and let only the lower slit be open, again you shoot particles one by one at a time. So again, they will come and settle on, and they'll form a pattern on the screen. So it's very clear that if they pass through the lower slit, they form this kind of a pattern, and if they pass through the upper slit, they form this kind of a pattern. But what happens when you open both the slits? You would expect that you will just get a sum of these two patterns, because particles which pass through the upper slit, they will form one pattern, and particles which go through the lower slit will form another pattern. But in reality, what happens is completely different. You will get this pattern where you have particles in some region, and there are some regions where there are no particles, and so on, alternatingly. So they form this kind of a pattern. So this is very strange because particles are not interacting with each other. We are throwing only one particle at a time. So somehow, for a particle, it matters if it is passing through one slit. It matters to the particle whether the other slit is open or not, because we saw when the other slit was closed, it was giving you another pattern, but now when the other slit is open, it is giving us another pattern. So this is something very, very strange. And this experiment it has was done actually long back, but people have still been doing more experiments on this. Latest one is this. I think first one was done in 1989, and this latest one is in 2018 scientific reports. So you can see that this is a picture of the screen, and these dots are these electrons which are falling one at a time. So, and you try to find out which slit each particle goes through. It turns out that as soon as you have a mechanism in place which finds out which slit the particle goes through, the interference pattern goes away. And what you get is exactly what you had initially expected, the sum of these two spread out patterns. So you will get kind of a homogeneous distribution of this on the screen. So this phenomena is really very interesting, that if you do not know which slit the particles are going through, they will give you an interference pattern. If you find out which slit each of them goes through, then this interference pattern is gone. So Bohr was so